All right, so I had a request for kind of talking through what these first and I'm going to do the second derivative chart look like. Thought that would benefit people. So I'm using 5 from your Unit 5 Worksheet 1. So the directions say that for each of the problems that you have, to include a chart, intervals of increase and decrease, x values of any maximums, minimums, and plateaus. For the second derivative test, include a chart, intervals of concavity, x values of any points of inflection. I'm going to create those charts for you, talk through them, and have you do the intervals on your own. So for the first derivative test, didn't mean to move that. For the first derivative test, we need to take the derivative. Okay, and so I'm going to my equation here. Just a nice basic power rule. So I'll have negative 3x squared minus 6x. Derivative of 5 is 0. Now from there, I need to set it equal to 0 and solve. So I've got negative 3x squared minus 6x equals 0. Hopefully you're recognizing, and this is one of the things that a lot of people won't think about right away, you can factor this to solve. So I'll take out a negative 3x, and when I do that, I'll be left with 1x and then a plus 2, because I divided both of those negatives by negatives. So once I've factored, I can set each of those equal to 0 and solve. So I have negative 3x is equal to 0, and dividing both sides by negative 3, I get x equals 0 as one of my values. And then I can set x plus 2 equal to 0. Subtracting 2 from both sides, I can get x is equal to negative 2. So from here, what I'm going to do is create my first derivative chart and what that's going to look like. So I have x and f prime of x. And then I'll have negative 2 and 0. Across from each of those, I'm going to put a 0 because the value of the derivative at those two x values is 0. And we know that because we found these values by setting the derivative equal to 0. So now my next step is to figure out what is happening before negative 2, between negative 2 and 0, and after 0. And the way that we're going to do that is we're going to choose values, numerical values that are less than negative 2, between negative 2 and 0, and then greater than 0. So what I'm going to choose, and I'm just going to use as friendly numbers as possible. Let's see, I might do f prime of negative 3. I'll do f prime of negative 1, and then f prime of 1. And I'll find out if those values are positive or negative, which will enable me to complete my chart. So let's start with f prime of negative 3. So that means I'm going to take my derivative, negative 3 times negative 3 squared minus 6 times negative 3. Simplifying, negative 3 squared is 9, times negative 3 is negative 27. And then 6 times negative 3 is going to be negative 18. Subtracting a negative is the same as adding a positive, but that'll end up giving me negative 9. So that means over here, I would put a negative to indicate that those values will make the derivative negative, anything less than negative 2. Then the next one I'm going to try, I'm going to evaluate the derivative at negative 1. So negative 1, negative 1, negative 1. Negative 1 squared is positive 1, times negative 3 is negative 3. 6 times negative 1 is negative 6. Subtracting a negative is the same as adding a positive, so I get a positive value here. And then finally, if I want to evaluate this at 1, I'll have -3 minus 6, which is -9, so a negative value. So let's talk about what this tells me. Okay, so looking at my chart, I now know that my derivative values, the slope of the tangent line is negative up until -2. That means, let me get myself some space here. Oops. That means that the graph is headed down, okay, from -infinity to -2. The slope of the tangent line is positive between -2 and 0. So the original function, that cubic function that we started with, is going up. And then after 0, the slope of the tangent line is negative again. So I know that my graph decreases, increases, and then decreases again. Okay. Also, if it goes down and then up, I know that I have a minimum at -2. And if it goes from going up to going down, I have a maximum at 0. I have no plateaus in this function. A plateau would look like it going from negative to negative or positive to positive, where it like pauses for a moment and goes horizontal before continuing in the same direction. Okay. So this is the first derivative chart we're looking for. The other things that we're looking for are the charts like we said. So this would be increasing from -2 to 0. Notice that this is an interval, not a point. It starts increasing at -2. I have parentheses because it's not including -2. If it were including -2, I would have brackets. And it's increasing until 0. And then it is decreasing both from -infinity to -2, along with from 0 to infinity. Okay, so that's my first derivative. Everything we'd be looking for, other than stating that it's got a max at x equals 0, and it's got a minimum at x equals -2. Now, what I want to remind you of is what we are describing is this original cubic graph, which looks like this. So here's what we found out so far. We found out that this minimum is at x equals -2, and that this maximum is at x equals 0. Now, if I wanted to find the y value to go with those x values, remember we can always find the corresponding y value for a function by going back to the original. So if I wanted to find what point this occurs at, I could plug -2 into that function to find the y value that corresponds. If I wanted to find the y value that corresponds to x equals 0, I could plug 0 into this function right here, and I'd be able to find the actual point on that graph. So now let's talk about the second derivative test. Now, second derivative test, we need the second derivative. So I'm looking back at my first derivative. I'm going to go one step further. So the derivative of -3x squared will give me -6x, and the derivative of -6x is just -6. From here, the process is exactly the same. And I'm going to set it equal to 0 and solve. So add 6 to both sides. I'll get 6 is equal to -6x, and dividing both sides by -6, I'll get x is equal to -1. That's the only value I get in this case. So I set up my second derivative chart, so I need to label it to show exactly what it is. At -1, the second derivative is 0. So I'm going to choose friendly values. So I'll evaluate the second derivative at -2, and I'll evaluate the second derivative at 0 to see what I get. So second derivative, -6 times -2 minus 6 is going to give me 12 minus 6, which will be 6, which is positive. So that means that my graph is concave up from -infinity to -1. And then if I evaluate the second derivative at 0, I'd have -6 times 0 minus 6, which is -6, or a negative value. So again, what that tells me, if I'm talking about my intervals, is that my graph is concave up, meaning that it's shaped like a cup. It could hold water. And it is concave up from -infinity to -1. It's concave down from -1 to positive infinity. Concave down means it's like a hill, like the water would roll off of its back. Okay. It's got a point of inflection at x equals -1 to find the y value. So if it's looking for the y value, we would plug -1 back into this original function. Now I want to talk about what concavity looks like on the graph. Concavity, so here's what we just found. We found that right here at x equals -1, we change from being concave up, so this part is concave up. It could hold water. Okay. It also makes a smiley face, concave up. Okay. Versus over here, it wouldn't hold water. Water would roll off its back. So over here we're concave up. Over here we're concave down. And it changes at x equals -1. All right, hopefully you found this helpful. If you have any extra questions, please post them to our question document. Have a great day.